All right, our final lesson in our similarity unit is an exploration of similarity in right triangles, and then also seeing what happens if we cut the sides of a triangle or bisect an angle in a triangle and create proportional segments. So as we explore these ideas, we're going to have to use our imagination a little bit. The first item on the list is probably the toughest because it requires a little bit of visualization, and probably one of the best approaches to find success here is to draw and redraw the triangles, but keeping a special focus on the angles. If we understand the angles in the right triangles, where they're located, which angles are congruent, we can then determine which sides are proportional much, much easier. The other two items, I hope that those are pretty straightforward as we have our conversation, but if they're not, then we'll just do some extra examples in class. But we should be able to create some proportions based on what we are able to see as we cut this through the sides of a triangle, or as we bisect an angle in a triangle. And so this is all about congruence within triangles. And the first part deals with right triangles. And so what we're saying here is if we draw an altitude from the right angle in a right triangle to the hypotenuse, what happens is we actually create two new triangles that are similar to each other, but also to our original triangle. So when we draw in this altitude, from the right angle in a triangle to the hypotenuse, we create two triangles that are similar to each other, but also similar to the original triangle. And focusing simply on the angle-angle similarity shortcut that we talked about in our last lesson, this is a right angle here, and so it gets cut into two pieces. Well, these angles are complementary, meaning that they add up to 90 degrees. In this right triangle, right, we drew this perpendicular. In this right triangle, this angle, let's say it's 30 degrees, let's say it's 40 degrees, it doesn't matter. It is going to be complementary with this angle. So these angles have to be congruent to each other. And likewise, in either this triangle, the medium-sized triangle, if you will, this angle has to be complementary with that angle, all right? Which means that these two are congruent. We can also see in the big triangle that this big triangle has a right angle. It has an angle that's marked twice, if this was like the 60-degree angle or the 50-degree angle as we talked about earlier. And then this is the 30-degree angle or the 40-degree angle as we chatted about earlier. We know that they add up to 90 degrees. And so if I say that this is x and this is y degrees and they add up to 90, then this has to be y degrees and this has to be x degrees. And so we find out that we actually have three triangles: the big one with the little angle, the double angle, and then the right angle. We have a medium-sized triangle with the little angle, the double marked angle, and the right angle. And then we have a smaller sized triangle with the little angle, the double angle, and the right angle. If we can redraw our pictures so that we can identify which sides correspond where, the key to this is not trying to figure out which sides necessarily go where. It's to start with the angles, and then from there we see the arrangement in the pictures to say hypotenuse goes to hypotenuse goes to hypotenuse, and longer leg to longer leg to longer leg, smaller leg, smaller leg, smaller leg. All right? And so we could label these with A, B, C, D, and we're not going to do that right yet. We're just going to apply this idea as we work through an example. So here is just a little other explanation of which sides go together. When we redraw those triangles, as I just showed, we find out that AB and BC and AC are the hypotenuses in these three triangles. So AB is the hypotenuse of the large triangle, whereas AC is the hypotenuse of the medium-sized triangle. BC is the smaller leg of the big triangle, whereas CD is the smaller leg of the medium-sized triangle. CA is the longer leg, the longer leg of the big triangle, and then DA is the longer leg in the medium-sized triangle. So we're just talking about these two triangles, the medium-sized one right here, CDA, and the big right triangle, BCA. Right? That's what we're doing here, is comparing the big one to the medium-sized triangle. In this next set, we'll notice that we have AB, again, the hypotenuse of the big triangle, and then we have CB, the hypotenuse of the little triangle. They go together. Segment BC in the big triangle is actually the short leg of this big triangle, whereas BD is the short leg in the little triangle. Right? And then CA is the long leg in the big triangle, and then DC is the long leg in the small triangle. So this is comparing the biggest triangle to the medium triangle. This is comparing the largest triangle to the smallest triangle. And then we have one more set that's going to compare the medium-sized triangle, that's this one right here, to the small triangle, which is this one right there. And so you can see which sides go with which sides. This is very tough when we're using this notation from Unit 1. The length of segment AB goes with the length of AC, or is proportional to the length of AC. In the same way, the length of segment BC is proportional to the length of segment CD, et cetera, et cetera, et cetera. And so let's kind of see what this looks like when we actually put numbers behind it. One more thing is that we're going to show you this relationship as we explore it in a situation where we can redraw this triangle using a little bit of animation. So here, we want to figure out what x is, and the way to do that is to recognize that between this small triangle and this medium-sized triangle, as part of the whole big triangle here, the smaller part and the medium-sized part have this relationship where this is the short leg of the small triangle, and this is the short leg of the medium triangle, right? And then on the other view here, right, this is our right angle. So these are the hypotenuses for the small triangle and the medium triangle. This is the long leg of the medium triangle, whereas this x is the long leg in the small triangle. So what we find out is if I compare the short leg of the small to the short leg of the medium, then I will get the length of the long leg of the small triangle compared to the long leg of the medium triangle. All right, so that is our proportion. Before we try to solve that, let's kind of visualize what happens when we do a little bit of rotation here. So when I'm talking about this is the small triangle, this has a short leg of 2 and a long leg of x. Short leg of 2, long leg of x. In the blue triangle, which actually I can make red, the short leg is an x and the long leg is 6. Short leg, long leg, short leg, long leg, short leg, long leg. So short to short, long to long. And so that shows us through a little bit of animation movement here that we can be comparing 2 to x and then x to 6. And that's how we build our proportions. It's a little tough to manipulate visually. All right, but when we do that algebra, if I go back here and click through this, we'll find out that the algebra here is a little tricky because it's going to require that we know how to multiply x's to get x squared. And while we recognize that that is a challenge, what we do remember from previous units is how to simplify radicals, how to take square roots. Now, in Algebra 1, if we were to take the square roots of both sides, we would have to consider a positive and a negative square root here. Obviously, we're not going to have a negative x value. We can't have a negative number as a side length, so we're only going to consider the positive or the principal square root. We do need to simplify that radical with its perfect square factor and the remaining factor. So square root of 4 and square root of 3 make the square root of 12, or the square root of 4 is 2. The square root of 3 we cannot simplify. So we find out that the length of that segment is 2 square roots of 3. All right, on to the next part, we'll see another example with that. And here we have x's and y's, and it can be pretty overwhelming. And so what we want to make sure we do is, first of all, we can find the y in the same way that we just found x on the previous slide. 12 over y equals y over 4. All right, that's kind of the easy approach and the easy memory there. But I think it might be valuable for us to think about those angles, as I talked about a couple slides ago. This angle here is congruent to that angle there. And this angle is congruent to that angle. And then all of these are right angles, and big triangle, right angle. So what we might benefit from is drawing the big triangle, the medium triangle, and the small triangle all together, where we have the right angles all arranged the same direction, the single marked, smaller angle marked, all in the same direction, and then the double marked angle all in the same place. All right, now what I mean by that is if we're looking at the big triangle here, we know that between the right angle and the double marked angle, included the side between these two angles, the right angle and the double marked angle, is x. And we know that the hypotenuse between the 1 mark and 2 marked angle is 12, and 4 together makes 16. In the medium-sized triangle, right, that's this one right here, between the 1 marked once and the right angle is 12. The 1 marked once and the right angle is 12. The hypotenuse in this medium-sized triangle, I don't know. Between the single marked and the double marked, I'm not going to have that side labeled. I don't know what that is. Just like I didn't know the long leg of the big triangle, I'm not going to know the hypotenuse of the medium triangle. Between the double mark and the single marked angle in the medium triangle is y. In the smallest triangle, between the right angle and the double mark is 4. Between the hypotenuse in our small triangle, or between the double mark and the single mark in the small triangle, is x. And so we can kind of see how we might be able to build a proportion here to try to find the values of some of these variables. And so what we want to make sure that we can understand is how these go together. So the first thing that I left off was in this small triangle, I was covering it up with my hand so I didn't see the shadow there, is that the long leg between the single mark and the right angle is y. All right, so my bad for forgetting that. But what we can do is compare the big one to the small one to solve for x. I've got the hypotenuse in both, I've got the shorter leg in both. So 16 over x is equal to x over 4. And then for the y's, I've got the long legs, 12 and y, and then I've got the short legs, y and 4. So this is big to small, big to small, big to small, big to small, medium to small, medium to small. Cross multiply and solve. 16 times 4 is equal to x times x. Take the square root on both sides. 12 times 4 equals y times y. Take the square root on both sides. We have to simplify that radical. This is 16 and 3, which gives us 4 square roots of 3. All right? So we can go through that process to create our pictures. By having the pictures, we can create our proportions, and then we can solve by cross multiplying. When we multiply a variable times itself, we get that variable squared. Okay, that was kind of the first part, and that was a little bit of a lengthy introduction. That was the lesson 4. Now we're going to move on to the last part, and this is going to take us a few slides, a couple more examples, probably about 6 more minutes of video. So the side splitter theorem is kind of amazing. It basically says if you draw a segment that is parallel to one of the sides of a triangle, passing through the other sides, it cuts those sides proportionally, meaning that this part and this part will be cut in the same way as this part and that part are cut from each other. And it's kind of an exploration of that notion. What we had before was that this part over that part, because these triangles are similar by angle similarity, and this give us a proportion. So this part over the whole side, this part over the whole side. But what we found out using rules of proportions is that we can subtract off this piece and subtract off this piece from that whole thing and just show that this part over the little part is equal to the big part over the little part on that side. Kind of an amazing thing as we have that exploration. So here's what we can write down from this situation. Segment AC over segment DC is equal to segment BC over segment EC is equal to segment AB over segment DE. That's what we did in our classwork 2 from the previous lessons, 8.2 and 8.3. But the punchline here is that this part is proportional with this part in the same way as this part is proportional with that part. All right? AD over DC is equal to BE over EC. All right, and so those segments will be proportional with each other. All right, recognizing that we can subtract off those parts from the whole numerator or denominator. All right, and so in this particular case, these questions end up being pretty straightforward. In this case, if we're going to solve for x, we don't have like the whole side length and the whole side length here that could really kind of confuse us when we're trying to find out what this remaining little piece is. So the easy way to do that is to say 16 over x is equal to 10 over 5. We cross multiply to solve, find out that 80 is equal to x times 10, divide both sides by 10, and find out that x is equal to 8. All right, it's a pretty straightforward approach. 16 over x equals 10 over 5, and so that is our proportion, and we can go from there. The next piece is the angle bisector theorem, and this is pretty fun. This is where, but it can be a little confusing, and it's a little hard to prove this theorem, but basically, if we cut this angle in half, then we create segments that are proportional to the other sides of the triangle. It's kind of a beautiful thing here. We would say that AC over AB is equal to DC over DB. We can also say that AC over DC, that this part over that part, is equal to this part over that part. In fact, that's what we will mostly say, is that this number over that number, or this length over that length, is going to equal this length over that length. All right? These parts over those parts. All right? It's, I think, a little less confusing, and you have a number here, a number here, a number here, a number here, make a fraction, and then you've got your proportion. All right? So in this case, we're going to say 12 over x is going to equal 10 over 6. So draw that picture, and you're going to have 12 over x equals 10 over 6, and you can cross multiply to solve. 6 times 12 equals 10 times x. Divide both sides, and we find out what x is equal to. So the math there isn't hopefully super challenging, but again, if it is, then we're going to want to make sure that we do a good job of talking through that, working through that. Put your questions in your notes, and then we'll discuss it in class. All right, so those were the shortcuts. I'm sorry, not the shortcuts, but the triangle congruence within triangles when we cut a right triangle with an altitude from the right angle to the hypotenuse, when we split the sides with a parallel line in a triangle, or when we split an angle using an angle bisector in a triangle. We create proportional segments.